Started. Please find your seats. Thank you. So thank you very much for coming to tonight's lecture. My name is Fadil Santosa. I'm the director of the Institute for Mathematics and its Applications. The Institute for Mathematics and its Applications, the IMA, is a National Science Foundation institute. It is located in Lynn Hall on the east bank of the campus of the University of Minnesota. Established over 30 years ago, the IMA is a research center where mathematicians work closely with scientists, engineers on problems arising in fields outside of mathematics, such as physics, chemistry, biology, and engineering. I'm very pleased to introduce tonight's speaker, Professor Brian Conrad. Brian is a professor at Stanford University. Before that, he was a professor at the University of Michigan. He did his undergraduate degree at Harvard University. He received his PhD from Princeton University in 1996. Doing his doctoral work under the guidance of Andrew Wiles, who is well known for his proof of Fermat's last theorem. His mathematical specialty is number theory, which is the study, roughly speaking, the study of integers. An example question that might come up in his field is which numbers are sums of two squares? Is 7 the sum of two squares? Is 25 the sum of two squares, etc.? And what are the properties of such numbers? Among mathematicians, number theory is considered one of the most difficult research areas. Among number theorists, Brian is considered a rock star. He's author of a number of seminal research papers and a couple of books. And I think you'll enjoy tonight's lecture, which is on the mathematical concept of symmetry and its applications from Rubik's Cube to internet security. Brian?
Okay, thank you very much. Does that make the lights go down? All right, so thank you very much for the introduction. So I'm going to discuss several aspects in which symmetry can be thought of sort of from a mathematical point of view in ways that actually tell us interesting things about concepts that we would have wanted to think about even if we didn't know about those mathematical features. And so the examples will be related to Rubik's Cube and some artwork of Escher and to secure communication on the internet, which has recently been in the news in some unusual ways, but we'll come to that later. So I want to begin with this quote from Hermann Weyl, who was a great German mathematician. And so Weyl felt that symmetry, we often think of it in terms of maybe some artwork or some nice the way a picture looks or a mountain. And he felt that symmetry was really one of the most ideal concepts in which one can really see the power of mathematics to illuminate interesting things that we would really want to think about even if we didn't know about those mathematical aspects, as I said before. And so the first thing I want to discuss in the talk through several different examples is to convey what do you mean mathematically by symmetry. And then we're going to illustrate it with a few examples. So we'll discuss a bit about Rubik's Cube, and not in terms of tricks to find a 20-second solution and that kind of stuff, but more in terms of whether there are certain general principles that we can think about from the viewpoint of the mathematics of symmetry that help us to understand certain properties of solutions to Rubik's Cube. And then we're going to focus on a couple of pieces of artwork by Escher. So this one on the left here is called Circle Limit 1. So these are blackbirds and white birds that are arranged in a somewhat complicated pattern, which becomes ever smaller as you go out to the boundary. And we'll see it's a sort of interesting question to try to describe precisely what's going on and what's the rule that generates this rather complicated looking picture. And then there's this other piece of work by Escher, which has a guy standing in an art gallery looking out a window, and then you have this veranda, and if you follow it around, well, okay, in this case, he tried to make it sort of loop back into itself, but then he got confused, and he didn't know what to do, so he just put his signature in the middle here. But we'll see that the mathematical principles of symmetry can actually help us to understand what actually goes in the middle, and we'll sort of figure out how to fill in that hole. And in fact, although these look quite quite unrelated, we'll see that from the viewpoint of the mathematics of symmetry, there are some similar features in these two pictures. And in particular, the math behind this one is actually quite relevant in explaining what's going on whenever you use a smart card, or if you open a bank account in a bank that you've never actually physically been to, and you sort of trust that it all somehow works, unless you work for the NSA. But anyway, so I want to begin with maybe one of the more famous examples of symmetry. So a few years ago, I went on a trip to India, and for a couple of days, I took a sort of a side trip to this city of Agra, which some of you may know about, and those who don't will recognize this picture. And so, of course, you have to ignore the people here kind of break the symmetry, so we pretend they're not there. And we look at the Taj Mahal itself, and we see if we imagine drawing a straight line down the middle, there's some sort of two-sided symmetry that if you flip the picture around itself, where you imagine it was like a huge mirror here, the part that's on one side, the reflection, you see exactly what's on the other side. So there's some kind of two-sided symmetry of the whole situation, minus the people. And what we're going to see is that if we take a closer look at the Taj Mahal, both in terms of the building as well as some of the floor patterns, there are much more interesting symmetrical patterns which exhibit some very nice mathematical structure, which we'll come back to later when we look at Escher and some of the other applications. So the first thing I want to do before we look more closely at the Taj Mahal is I want to describe in somewhat different terms this idea of reflecting. In this case, if we talk about reflecting the picture across a line, we might think in terms of reflecting through a mirror, but I want to describe that in terms that don't make any reference to mirrors, because later we're going to see manifestations of this in other situations where talking about a mirror might not make any sense, but the mathematical description will. So we want to think about this idea of what does it mean to reflect through a line. Okay, so imagine we draw a line, okay, and we're going to have a point on one side of the line, and then if you imagine, then we want to think there's a point diametrically opposite on the other side, and I want to describe the process of going from this point and producing this point in some way that makes no reference to mirrors. Okay, and so the way we'll do it is the following. So we pick a point P, and what I'm going to do is I'm going to describe the process of computing the point on the other side purely in terms of our notion of distance. Because later we'll see there are other situations where there's a kind of reasonable notion of distance, which is not quite the usual one, but as long as we have a recipe purely in the sense of distance, then if we modify our notion of distance, we can modify our notion of reflection across a line. First of all, by the way, a line itself can be characterized in terms of distance. Right? A line is nothing more than a path with a property that for any 2 points on the path, the part of the path between them is the shortest distance between those points. Right? So we can characterize lines in terms of their distance minimizing properties. And in terms of reflecting a point across the line, so what we do is we choose the point on the line closest to this, which minimizes the distance. In that case, it's kind of perpendicular. And then having found that point that minimizes the distance to our guy, then we draw the unique line through those two. Okay, so then we get that new line through these 2 points. And then what we do is then on the other side, we just go the same distance as there was to here. Right? And then we get our new point P prime. Okay? So once we've set down what our notion of distance is, minimizing distance gives a notion of line, and then for any point off the line, we can compute the point on the other side just by certain operations that are expressed purely in terms of our notion of distance. Okay? So you don't need to say anything about mirrors. All right? And so we'll revisit this later. But first, let's go around to the back of the Taj Mahal. And so, well, over here on the right is just some dirt fields. It's actually not very picturesque, so you don't really ever see it, so we'll block it out. And so on the floor back here, there's some kind of interesting pattern, these alternating dark and light regions. But there's this kind of effective perspective into the distance, which you want to get rid of. So I'm going to draw a kind of idealized cartoon image. So it's these same little patterns, but in this version here, I've gotten rid of the effect of the shrinking from the perspective. Okay, so here's the floor pattern. And so, of course, the dark regions are some shape that repeats itself, and the white regions. And then we ask ourselves, are there some kinds of reflections we can make on this figure which will bring it back to itself? Okay? And if you take the center of any of these dark regions, and you draw either horizontal or vertical lines, or these diagonal lines, right? And if you sort of visualize it in your mind, if you choose any of these lines and you take what's on one side and you reflect across to the other side, you see you get back exactly the original picture. Okay, so in that sense, this floor pattern has a kind of four versions of two-sided symmetry. Okay, so there are these for these both the dark and white regions. But on the other hand, it's not any old four lines. Okay, here we're connecting these opposite vertices. If you try to connect the midpoints, it does not interact very well with the geometry of the shape in the middle. Okay, so these are not just any four old lines; they're in fact tightly connected to the geometry of the dark regions. In any event, so this floor pattern has four different instances of this two-sided symmetry, which is much more than you can say for the Taj Mahal itself. Okay, but there's more. Okay, which is we can rotate. We have rotational operations that also carry the picture back to itself. So instead of just reflecting through these lines through opposite corners, if we rotate the figure 90 degrees, it also comes back to itself. And again, that has to do with the geometry of the dark region. And of course, you can keep doing that, 180 degrees and 270 degrees. And that's clockwise. Of course, if you wanted to go counterclockwise 90 degrees, you just do the clockwise version 3 times. Okay. So if you start taking these 90-degree rotations, then you can get 4 more versions of, you get 4 instances of rotational symmetry. And yet there's more. Okay? Imagine the following. Take any of these parallel lines through the centers of the dark region, and if you take one of these and you translate the picture, and you also have these parallel these vertical lines here, if you translate it 2 steps over, again the picture comes back to itself. So in addition to the reflectional symmetry about certain lines and the rotational symmetry by 90 degrees, this also has this translational preservation as well. But in fact, and this is something that will come up again later, I claim that the translational symmetry, the fact that if you take this line and move it 2 steps over to this one, you come back to where you began, this kind of 2-step translational preservation is in fact already a consequence of having enough reflection symmetry. So sometimes if you have a figure that seems to be preserved under certain geometric operations, that alone can explain other geometric preservation as well. And to explain how it's possible that reflection symmetry gives rise to translation symmetry, we'll consider something that you see in, if you're in a bathroom that has mirrors on opposite walls, and you sort of play that game of trying to make it oscillate back and forth forever. So if you imagine this, so this girl here is sitting in front of this mirror, and of course she sees her own reflection. But if there's a mirror on the back wall, and then you look at the reflection within the reflection, then you see that the girl has kind of moved a distance sort of twice as far as the distance between the mirrors. Now, of course, you might think this is sort of artificial because that's not a real girl, right? That's just this kind of thing inside of a mirror inside of a mirror, so this is kind of fake. But this just illustrates, if you think about the light beams going back and forth, this picture that somehow the girl seems to have jumped 2 steps forward is in fact a manifestation of the same thing from the previous picture. So in fact, if we go back here, you'll see that if you actually take some of these lines and you start reflecting and reflecting, you'll see that in fact you can do this two-step motion. Okay? So let me just summarize what we've seen so far in the case of the Taj Mahal, and then we'll discuss these more interesting examples, the Rubik's Cube and these Escher pictures. So first of all, I want to make some kind of precise definition. So what exactly is meant by symmetry? So we want to imagine we have some configuration of pieces. They could be the tiles on the floor, or these arrangements of blackbirds and whitebirds, or the pieces on the cube with their complicated color arrangements. And so when we speak of symmetry, what we want to imagine doing is that we take the pieces and possibly just in our mind, or with the Rubik's Cube, physically with the cube, we're going to rearrange all the parts, but in such a way that certain properties have to be preserved. Okay? For example, we might want to, in the case of the floor pattern, think about rigid motions, so distances should be preserved. Of course, for Rubik's Cube, that's not the case. When you rotate one face of the cube, the distance between this piece and that piece changes dramatically. So distance preservation might be a condition you want or not, depending on your situation. You might want some preservations of angles or colors and so on. And the only condition that we're going to imagine imposing is for any of these rearrangements that we allow, any two, if you compose them with each other, you should get a third. Okay? So in the case of this floor pattern here, which was illustrated with that girl and the double reflection in the mirror, sometimes certain rearrangements, if you compose them upon each other, you get new ones that might look quite different. Okay, so the composition of any two symmetries is another symmetry. And anything you do, you should be able to undo. Okay? So if you rotate 90 degrees one way, then you can also rotate 90 degrees back. Okay, so any of these operations that you allow, you should also be permitted to do it in reverse. Okay, so that's what we mean when we speak about symmetry. And the thing I want to stress at the outset is that often it can happen, and we'll illustrate this in a moment, that the order in which you apply these rearrangements can have a huge effect on the net result. Right? If you ever tried to solve a Rubik's Cube following a book, and then you made a mistake at one point, and then of course it all becomes chaotic, then you realize the order in which you apply these rearrangements can have a huge effect on the composite result. Okay? Of course, the fact that the order in which you do things makes a difference, you can also think about by whether you try to enter a room before or after you open the door. But in any event, an interesting thing is in the case of smart cards, as we'll see, the symmetries that are hiding inside the mathematics of smart cards are examples where the order of composition does not matter. Okay? So it's quite different from the geometry of Rubik's Cube or some of the motions in the case of the back of the Taj Mahal. And in fact, the insensitivity in this case, we'll see, is quite crucial to why the security method in the smart card actually works. Okay, so let's now turn, having just made some kind of precise definition of what symmetry means, I want to discuss it in the case of Rubik's Cube, and in particular, try to clarify some features of solutions to Rubik's Cube by using the mathematics of symmetry in a way that makes sense far beyond the setting of Rubik's Cube itself. So this guy here is Mr. Rubik, and his discovery of this cube while he was an architecture professor made him the first self-made millionaire in communist Europe in those days. And in fact, it'll be quite interesting to see that, so in this particular case, the cube is, of course, quite simple looking at first, but anybody who's played with this knows that there's something very complicated going on in this puzzle. And when we speak of symmetries of the puzzle, what we mean are the rearrangements obtained by the usual so-called legal moves, that we take any face and we rotate it 90 degrees one way or the other, or we might take a middle slice and spin that 90 degrees one way or the other. What we don't allow is my preferred method of solving Rubik's Cube, which is the screwdriver method. That you take a screwdriver, you just jam it in there, you pop the piece out, and then you reassemble it. It's very easy. Okay? So that's not the kind of symmetry that we're going to consider. Okay? So no screwdrivers. All right. Now the first thing is, when you buy one of these, they try to impress upon you how complicated the puzzle is, because they say it has so many positions. All right? This many. All right, trillions, right? Very large number, except compared to the national debt. And this number here is not as structureless as it seems. And of course, you don't find this by, some nerd sitting in a corner counting pieces. Okay, there's a very clever combinatorial way to think about the symmetries of the cube, and the correct way to describe it is via this fraction. All right, with these little factorials here. I won't get into exactly how one finds this, but it involves a sort of deeper understanding of what's going on inside the cube. I just want to mention in passing, before I try to convince you that this is not as impressive as it seems, I just want to stress that in this description of the count, this denominator is actually the most interesting thing. That there are certain very non-obvious properties of the legal maneuvers of the cube, which are encoded in this. This is a naive count, which is an overcount by a factor of 12. And the fact that it's exactly a factor of 12 is a quite interesting mathematical argument, which I don't have time to get into. But the first thing I want to convince you before we actually say something interesting about the cube is to convince you the packaging is really misleading. Okay, so this large number of positions has nothing to do with why the cube is hard. Now, of course, you would say, that's ridiculous. That's a very large number. That must be the reason. So to convince you that it really is not the reason, that actually it's more related to the relationship between the algebra, the symmetry, and the geometry of the cube. But to convince you that you should ignore this, I'm going to discuss another puzzle that you will never find in any store because it's a really stupid puzzle, but it will have many positions. So we'll call this the alphabet puzzle. Okay, so what's the puzzle here? All right. So you can laugh, but anyway, just for illustration. So here's the puzzle. You imagine you have 26 boxes lined up in a row. And each one is filled with a letter of the alphabet in some way. And the puzzle, which is really dumb, is all you have to do is get everything in alphabetical order by swapping 2 letters at a time. Okay? Now this is not a very hard game, right? Because you just look for A wherever it is and you swap it with whatever's in the first spot, right? Put H there, and then whoops, sorry. There we go. And then you look for B, which is somewhere in here, and then you swap it with whatever's here, okay? And then you see, where's that? Okay, now H was moved here, and you put C in position, and so you just systematically go from left to right, looking for the correct piece. If it's already there, great. If not, you just swap it, okay? And so in this way, after 25 swaps, you've got the first 25 letters correct, and there's only 1 spot left, and so that's got to be Z, and so you're done. Great. So you only need 25 moves, and it's a very easy puzzle. But the total number of positions is 26 factorial, which is about 10 million times more than the number of positions in Rubik's Cube. Okay, so, and again, in fact, what's really going on here is the underlying algebra of the symmetry of this puzzle and the geometry are very closely related in a way that one can visualize. And that's somehow why, I mean, it's an easy puzzle without knowing any math, but I'm just saying that the contrast, even mathematically, can be seen if you think geometrically. Okay, so let's now discuss something interesting about the cube itself, okay, rather than the packaging. And so the first challenge is how to discuss it, because the problem is different cubes have different color arrangements, okay? So here's a picture of one, and you have orange on top, red on top, and then here's orange and blue, okay? And, or maybe that's orange, yellow, and blue, I apologize. Now here is, so I use my screwdriver method at home, and so here you see when you put orange on top, it's really a different arrangement, okay? Here the kind of the orientation of blue and yellow is opposite, okay? So when you want to discuss systematic thinking about the cube, you should not really use the colors, okay? So the best thing to do is to speak in terms of the geometry. You put the cube in some standard position like this, lined up on these 3 standard lines, and then we speak about the upside, the right, the left, if we're standing in one fixed position, the back, the front, and the bottom, which we denote D since B is taken for back. And if we want to describe a motion, right, well, if we think about 90-degree rotations counterclockwise, okay, that will give us all of the motions of these faces. And of course, if you do it 3 times, that gives you the other direction. Right? And in fact, if we discuss things in terms of rotation, 90-degree rotations of any of these 6 faces, in fact, if we think about it, we can use that to also get the effect of rotation in the middle. For example, if you want to take this middle slice and rotate it 90 degrees that way, then you can just take the parallel outer slices and rotate them 90 degrees the other way. And that has the same net effect, because physically moving the cube in space doesn't constitute anything, and we can kind of ignore that. Okay? So these 6 we'll call them the basic moves of 90-degree counterclockwise rotations in any of the 6 outer faces. If you compose those with each other, you will get if you just think about it, you would really get all of the possible motions that you would ever want to make on the cube, up to physically moving the cube in space, which does not really constitute doing anything. Okay? So those are the 6 basic moves, and we're going to see that if we think about those basic moves, they're going to tell us something interesting about the cube, about solving the cube itself. So now we come to this is related to the main problem. So I understand the math behind this, but I can solve one face, okay? But I have this psychological obstruction, which is, you see, of course, if you're going to get anywhere, you can partially do the second layer, but at some point you have to sacrifice all that progress and then come back and then hopefully get further. And when I see it start getting messed up, I get very disoriented. So in any event, so this is the big problem, right? That you can't solve it by just doing one layer at a time. At some point you have to step back and partially screw up what you've already done if you want to eventually get more pieces into position. And so I want to describe a basic principle behind doing this in a successful way that will illustrate an interesting mathematical principle that applies to quite general symmetric situations and has nothing to do with the Rubik's Cube, but will explain a certain feature of many common solution methods. And to illustrate that, I want to describe the following situation. So suppose by some miracle, you manage to solve it except for these 3 pieces, okay? And then you want to get to here. And the question is, how do you do that? Right? And Well, it's going to be easier to describe. Let me describe how you would go from the solved position to this one. And of course, you could run it in reverse. But there's going to be a certain feature of that process that will be quite interesting. And so to describe that, I'm going to define two composite motions, which we're going to combine with each other in a somewhat interesting way. So the first composite motion I'm going to call x. All right, so what's x? You start with the solved position, and then we take this front face, and we do 90-degree rotation clockwise. And then having done that, we take the top face, and then we're going to move it right this way. You see this side here comes over here. So that's 90 degrees counterclockwise. And then finally, excuse me, we take that front face again, and we move it back. Right? So before you move 90 degrees this way, now we move 90 degrees that way. Right? So this white piece here got moved. This red on top wound up over here. Okay? So the whole bottom, in particular, although part of the bottom got moved up, most of it came back. Okay? Except, well, this one piece got screwed up. Okay? So you're moving one face, and then the top, and then the other one back, and then you get to here. So this whole composite motion, we're going to call x. Okay. And now we're going to, one other motion we're going to call y, which is simply, excuse me, that you take the bottom side and then you rotate it 90 degrees counterclockwise if you were looking at it head-on from the bottom. Okay, so this is what we'll call x, and this is what we'll call y. Of course, even if this weren't solved, y just means take the bottom and rotate 90 degrees that way. Okay, so that's x and that's y. Now here's the interesting thing. If we apply x, and then we apply y, meaning take the bottom and move it like that, okay? Then we get this total garbled mess. All right, you think, well, that's not very good. But one thing I want to point out is that in this, excuse me, in this arrangement here, all right, there is only, although we've moved a lot of things, there's only one piece that actually got affected by both x and y, okay? And that's this bottom corner down here. Right? I mean, there are other pieces that got moved around, but all the rest that got moved either got moved only by y or only by x. All right? Because y took place entirely on the bottom, and the net effect of x, the only piece on the bottom that got affected was this one. Everything else, all the other junk was happening up here. Okay? So there are two different motions, and they have exactly one piece they affect in common. All right? And when you compose one on the other, you get a horrible mess. Here's something interesting. Having done x and y, and the order in which you do these makes a difference. If you then do the opposite of x, all right, and then you do the opposite of y, then in fact you get exactly the thing that we wanted. All right. So if you do x and y and undo x and undo y, what happens is you've wound up moving three pieces: this, this, and this. This is what we call a three cycle. You have all these pieces of the cube, and there are these three specific pieces. And you do this very complicated thing of an x and a y, and then the opposite of x and the opposite of y, and then in the end, you wound up moving exactly three pieces. And this might seem like some kind of total miracle of the geometry of Rubik's Cube. It has nothing to do with Rubik's Cube. Okay? You take any rearrangement of the parts of anything, call them x and y, with the feature that there's exactly one piece which is affected by both. And if you apply x and then apply y, and then if you do the opposite of x and the opposite of y, then it always happens that the net effect is to move exactly three of the pieces. Okay? This is just a general thing, and if you think about symmetry mathematically, in fact, it can be proved by a very short calculation. But the interesting thing is that if you look at systematic solutions of Rubik's Cube, they always have these kinds of motions over and over and over again, that you have two kinds of maneuvers, and then you do one, and then the other, and then you do the opposite, and then the opposite. Okay? And then, although it looks like a very complicated maneuver at each stage, the net effect is just to move three things, and that's a general feature of all symmetries. It has absolutely nothing to do with Rubik's Cube. You take any puzzle made from any pieces or any symmetric situation whatsoever, and this theorem is always applicable. Okay? And in fact, in the deeper study of symmetry, what's called group theory gives one a great deal of insight into the properties of these motions of the cube and actually explain what's going on in all of these solutions. Okay? So at least at a kind of very initial level, we can see that there is this kind of general principle about symmetry which explains at least one feature that one often sees in solutions to the cube. Of course, if you want to understand the more complicated solutions in complete generality, then one has to bring in much harder theorems in the mathematics of symmetry. But the point is, it's not some bag of tricks. Okay, there's a way of thinking about these things that applies to quite general puzzles. You just have to understand the special symmetries in your situation to come up with the appropriate solution. Okay, so that's Rubik's Cube. So now I want to discuss symmetry in a somewhat different situation. So this is the artist Escher. So he spent most of his life in the Netherlands, and he had no mathematical training at all, at least nothing beyond like junior high school or something. He certainly had never studied geometry in a very sophisticated way, but he had a great deal of geometric insight in his artwork, and he was particularly enamored of the idea of infinitely repeating a pattern within a bounded region. And some of his early artwork didn't exactly exhibit this feature. They required infinite repetition, off to infinite, off in both sides of the page. But later he came to focus on this idea of repeating something within a bounded region. So this was an example of one of his early works where things were kind of unbounded. So you have this one guy in white, and then you have this other guy with sort of darker colors, right? And then there's this third guy who is sort of more gray shape and more gray color in between. And these three pieces interlock in a somewhat complicated pattern, and it sort of continues up and down and left and right. Okay, so this is one of his earlier studies of what we call plane tilings, finding, it's very easy to tile the floor with squares or hexagons, like in the Taj Mahal, but you don't usually find the bathroom floor tiled with these funny-looking guys. Okay, so Escher was particularly good at coming up with these rather non-obvious tilings, but they require going off to really see the symmetry and the repetition. You have to go off arbitrarily far on the left and the right when you iterate it over and over again. And so we're going to analyze doing this in a bounded region. And so he was able to make partial progress, but at some point he got stuck. And we'll see this in the case of the picture with the blackbirds and the whitebirds. And somehow he fell into correspondence with this great classical geometer, Donald Coxiter, who was a professor in Toronto for many years. And in particular, at some point, Coxiter sent him the following picture. So here we have these green arcs, okay? And we have these dark regions and white regions. And notice, by the way, that so how many sides is this? They're curved, but 1, 2, 3, 4, 5, 6. Okay, so this is a did I count that correctly? 1, 2, 3, 4, 5. Yeah. So this is a hexagon. Okay, and these other regions also, in fact, if you count, these are also they're not normal-looking regular hexagons, right? The sides are warped, the angles are screwed up, and everything is getting quite tiny as you're going out to the boundary. So the geometry is a bit warped in some way, and we'll try to understand what's going on there. But there's some sense in which there's some kind of a repeating pattern, but it's hard to articulate exactly what's going on because the physical shape is changing, right? If we, in here, really, like this guy is the same as its counterpart here and here and here, all right? But in this picture, it's a bit harder to say what's going on. But Escher was quite impressed by this, that there's some kind of infinite repetition within this bounded region. He's trying to understand what was going on there. And in thinking about this, he kind of came up with this idea of trying to write down a bunch of blackbirds and whitebirds somehow lined up with these curved arcs. Right? The problem was he wasn't quite sure how to make these arcs when you get very close to the boundary. Okay, so how are you going to construct these tiny, tiny arcs? He could make this big one, but then he kind of ran into problems. So here was his clever method. So the first thing he did was, so he had this circle here, right? And then he drew this square, and then he figured out, he made he made these two big circles with the same radius as this one, and then he repeated the pattern around, and he was eventually able to make this hexagon in the middle. And then, well, he came up with some more and more clever, trisect this side and do some stuff. It got kind of complicated. And all right, so by the time he got to the fourth layer of arcs, he kind of ran out of clever tricks, and he just had no idea how he was going to produce these ever and ever smaller arcs. So he got really stuck. So then he sent Coxiter a letter, and he said, well, I could make the first 4 layers of this repeating pattern, and now here I don't know what to do next. And then Coxiter, with the brevity of a mathematician, he just sent back this little thing. He just drew a segment and a little circle, and that's all he said. So Escher wasn't very happy with that. And so one wonders, but eventually he managed to make the picture by some approximation process. And so then we wonder, what is going on, right? Like, how do we think about the process of starting with the big warped hexagon and generating these ever and ever smaller arcs? And I claim that, in fact, it's a curved version of some of the same geometric symmetry we saw at the back of the Taj Mahal. Okay, so let's see how that goes. So let's come back to the Taj Mahal, and instead of looking at the floor, in fact, we're going to look at a pattern on one of the back walls. All right, so this is a kind of window, and this has a kind of familiar hexagon pattern. These hexagons are regular, unlike the warped one in Escher's situation. And we can draw lines through opposite corners, right, 3 pairs, or through midpoints of opposite sides, 3 pairs there. These are 6 different lines, and of course the regular hexagon is symmetric around any of these 6 lines. Okay? But if we imagine taking one of those lines, like this guy, all right, and we extended it off, right, up and down like this, it goes through this side. So instead of thinking about flipping a hexagon through a line like this, we're going to think about flipping a hexagon across one of its sides. Okay? And so this is what we're going to do. We think about lines through edges of a hexagon. So we start with one hexagon, and if you start flipping it across an edge, or across this edge, and then take that new one and flip it across its edges, and do the same thing back here. And if you take the hexagon and you keep flipping through edges over and over and over again, you will generate this pattern of hexagons that exactly covers the plane. Okay? Well, that's great. That's this kind of reflection through a line, which we discussed earlier. We'll come back to that in a moment. And this idea that starting with one basic hexagon generates a tiling of the usual plane by reflection through edges, in fact, I claim, is going to explain exactly what's going on in that earlier picture that Escher was trying to understand. The difference is our sense of reflection has to change by using a different notion of distance, and our sense of hexagon has to change. We have to use some kind of curved geometry. Okay? And to explain that, I first want to compare the 2 pictures. So here's Escher's picture here. Here's the picture that Coxiter sent him. And here again is the middle hexagon, right, that he was able to construct. And we see that if we draw lines through midpoints of opposite sides, we break it into these 1, 2, 3, 4, 5, 6 regions. And he just drew these birds down the midpoints, these black birds and then white birds in this alternating pattern. Similarly, on this edge here, there's a black bird along the edge and a white bird here. So somehow he's lining up the birds along the edges. But the question is, how exactly are we generating these paths, these curved paths, starting with just this basic hexagon in the middle? Okay? And as I said, Escher could get that one, but mathematically, how do we generate the rest? Once we get this pattern, then we can lay down the birds, exactly along the arcs themselves. But how do we actually generate the pattern? Okay? And so to explain this notion of curved geometry, I want to explain another setting where one is more familiar with curved geometry whenever you travel on a plane. Okay? And this is going to relate to a familiar fact from elementary school, that you can't make a map of the Earth on a flat piece of paper which accurately reflects the geometry of the surface of the Earth. There's always going to be some distortion, possibly in distance, possibly in angle, maybe in both. That would be pretty bad. But you have to give up something. You can't accurately express these two. I mean, it's very important to compute distances, but if you're in a ship going somewhere, it's very important to know about angles, the angle that you're making to some direction. So these are both important features, and you would like a map of the Earth to accurately express at least one of these, but it's a theorem in math and geometry that you can't get both. All right? So this is the familiar Locator projection, and this has the advantage that it actually it expresses angles very well. So if you're using this map and you're in a ship or an airplane and you need to follow a 30-degree line to some parallel, this map is great. If you're trying to compare the area of Greenland to the area of Africa, or let alone Antarctica, right? Pretty bad, right? So like in the hotel that I'm staying at here, they have these many globes on the back, and it's very funny. You look at this globe and you think, gee, it doesn't look anything like that map. Okay? This is called the Lambert projection. This is not as popular a map. This one does not preserve angles, so it's not so good for navigation, but it does actually respect area ratios. So it accurately reflects the fact that Africa is about 14 times larger than Greenland, for example. Okay? On the other hand, it's a bit of a mess. Okay. So here's an interesting way in which the distortion effect of making a map can really be readily seen. If you think about the geometry of a sphere, if you're trying to get from one point to another point, the shortest distance is you basically imagine passing an equator, a great circle, through those 2 points. And you follow that great circle around between the points. That's the shortest path between 2 points on the surface of a sphere. But if you take a great circle between 2 points and you plot it on the Locator projection, right? Let's say you're trying to go from San Francisco to the Philippines or something, yeah? Then you do not get paths that look anything at all like circles, okay? And you have the familiar effect that you have to go through the North Pole, and so on the geometry of a planar map, the shortest distance between here and here would be the straight line. But in spherical geometry, length minimizing paths are these circles. And if you convert spherical geometry onto a flat piece of paper using the Locator projection, these are length minimizing paths. These are the kind of lines of spherical geometry, but on a plane, flat plane, they don't look anything like lines. Like this guy here, there's a kind of bend in the middle. Okay? So if you try to take curved geometry and express it on a flat piece of paper, then what should be length minimizing paths look very curved from the viewpoint of ordinary geometry. Okay, well, there's a variant of ordinary geometry called hyperbolic geometry, and that is what corresponds to the Lambert projection. Okay? And in hyperbolic geometry, one often can express things in terms of what's called the Poincare disk. So rather than using this flat piece of paper, we go back to the Lambert projection. Okay? Now the map of the Earth has been put onto a disk. Okay? And so if we use that, and we try to express the geometry of a ball on a disk, the so-called Poincare disk, then it's not going to be like this Mercator map. But again, these great circles, which look nice, will turn into certain warped regions. But these are going to be the length minimizing paths. And so it turns out that in the Poincare disk, in the Lambert projection, these great circles become exactly those funny arcs that we saw. Those are in some sense the lines of hyperbolic geometry. So in other words, if you take the geometry of a sphere or a sort of variant of a sphere called a hyperboloid, and you express it in the language of a flat disk, then the lines that look length minimizing on that surface, which is not quite a sphere, when you put them on the disk, they become these guys. So these are the length minimizing paths of a different theory of geometry called hyperbolic geometry. And if you take this region, and so it gives you a different notion of distance called hyperbolic distance. But we discussed at the beginning that once you have a sense of distance and you have a sense of length minimizing paths relative to that notion of distance, then there's a way of describing the act of reflecting across one of those lines. Okay? And if you apply that procedure in this situation to this hexagon in the middle, and you reflect it across this kind of hyperbolic line, you'll get exactly this hexagon here. Okay? And so this reflection process, in the sense of distance, makes perfectly good sense in this modified theory of geometry. And in fact, that reflection principle generates the entire pattern. So this is the hyperbolic geometry analog of the hexagon pattern at the back of the Taj Mahal. Okay? So if you do this, you get that repeating pattern. Okay? So here's a practical application. When you're making pancakes, okay, if you want to squeeze a lot of pancake into a disk pan, then all you have to do is use the Poincare disk model, and then you can make as many pancakes as you want. Well, maybe. Okay. So this was actually a real cartoon. Okay. So the guy who made this is a physicist, and he used to be a physicist. He has a PhD in physics, and they use this Poincare model, so he knew about that. But it doesn't actually work out so well. Okay. In any event, so the thing I just want to stress is thinking about the idea of reflection in terms of symmetry. If you bring in geometry, it explains this reflection pattern. So although from the viewpoint of ordinary geometry, this doesn't really look so symmetric, from the viewpoint of hyperbolic geometry, this is as symmetric as the hexagon tiling of the plane. Okay? And that's exactly what's going on in the pattern that Escher was trying to understand. Okay, Great. And I want to now turn to the manifestation of symmetry in a different picture made by Escher, the so-called circle limit. Okay? So here again is the picture of the guy in the gallery, and he's looking, and it kind of tries to feed back into itself. But as I said, Escher kind of got confused here. The Dutch mathematician Lenstra was on an airplane flight once, and he saw this in a magazine, and he wondered to himself whether one could do a better job of filling in what goes in the middle than Escher had done, where he got himself totally confused. Right? You sort of see some kind of spiral, but what's really going on there? Whoops, sorry. So he kind of thought about this for the rest of the flight, and then when he got home, and well, earlier, so Hofstadter in his book Gödel, Escher, Bach had actually discussed this problem, and he claimed, God knows why, impossible! You can't do it. You see, there's some mumbo jumbo about the Gödel incompleteness theorem, blah blah blah, and you can't do it. Impossible. All right, gibberish. So Lenstra figured out how to use an idea of the mathematician John Tate from Harvard. And he had a brilliant idea in 1959 related to the theory of elliptic curves. And I'm going to illustrate this in a moment with a movie. So in number theory, in the theory of elliptic curves, people had run into this kind of spiral pattern in a completely unrelated situation. But Lenstra, being a number theorist, knew about this, and he realized that Tate's ideas provided exactly what was needed to figure out what goes on in the middle. And just as the first Escher picture was a kind of curved geometry version of the familiar hexagon tiling of the plane, we're going to see that what's going on here is a different kind of curved geometry version of another familiar fact from ordinary geometry, which is this idea of a picture within a picture within a picture within a picture within, right? And here you see if you draw the lines through the common vertices, they're kind of converging to a point in the middle. And so here there's another kind of spiral going on. So that was the key insight Lenstra had. By using elliptic curves, these are not ellipses. Okay? They're much more interesting kinds of curves, and they have a much more subtle kind of symmetry, which we will see a little bit later when we come to internet security. But he realized that the subtle symmetries of elliptic curves could allow him mathematically to fill in the hole. Okay? And he did this in joint work with two other mathematicians. And so let me first show you. So this is the so this was Escher's picture, and by following purely mathematical rules, they made the completed version. I'll show you a movie of this in a moment. And so you see, Escher, even though he didn't know anything about the theory of elliptic curves, he came pretty damn close. He did a really, really good job of this. But let me now show you the movie that illustrates this spiral pattern. So let's pull up the movie here. Screen. Let me just make sure that was on the loop mode. Good. Okay. All right. So now this is going to be like a little bit psychedelic here. All right. So let me just move. There we go to the beginning. All right. So here we go. So we're spiraling in. All right. And where's the guy? Where's the guy? Oh, there he is. All right. Whoa. All right. So let's watch that again. Okay. Now watch. Okay. So let's try this a little more times. Okay. So all right. Where is he? Where is he? Where is he? Ah, there he is. Got him. Okay. So anyway, so there are websites that you can do, and you just watch this all afternoon. Right? It's kind of mesmerizing. And actually, the website that they have, you can put in your own pictures. And anyway, it's really kind of cool. All right. So we'll end with that. So that was good. So I did not make that movie, of course. They made it themselves. But anyway, all right. So let's come back to the. Wait. How do I? Right, so that was that picture. Okay, so we see that in this in the Escher situation, it was the theory of elliptic curves. I'm not going to define, but I'll show you some examples later. But there's a completely different theory of symmetry, totally different kind of curved geometry than in the other situation. But it's kind of working in this picture in a very interesting way. All right, but in fact, those elliptic curves, that other kind of warped geometry, in fact, is hiding inside your smart card. Okay, which sounds unbelievable, but it's true. And so let me just set the stage by describing the basic conundrum that you have to solve in order to actually have commerce over the internet, which is the following puzzle. You're trying to buy something from a company right? And you send them your credit card information, and you've never physically met them, and yet you want to set up, or you believe, you set up a secure link with them in such a way that, you know, the scam artist who's tapping into the line cannot somehow interrupt the discussion. So you want to somehow set up a secure link without ever exchanging directly the encoding information. Right? And during World War II, this is a huge problem, right? They had people running all over the different, the German submarines and so on to exchange next month's code books. Total mess. And you've never exchanged a code book with Amazon, right? And so somehow there's this kind of, you know, it just seems hopeless. How can you establish secure and encrypted communication without ever directly exchanging an encryption scheme? And so these three gentlemen here, Whitfield Diffie and Martin Hellman and Ralph Merkle, they figured out a very clever idea using number theory, and eventually it was called public key cryptography, to actually, you know, achieve the unachievable, okay, to make it possible to do secure communication without direct contact beforehand. And so later on, these three gentlemen here figured out a modification of the earlier scheme, which in fact used somewhat harder principles in number theory to pull it off. And the big breakthrough in the mid-'80s, Victor Miller and Neil Koblitz came up with what's called elliptic curve cryptography. And this was a more sophisticated version of what these guys had done. And this really made it possible it was an improvement on what these three did, in the sense that the theory of elliptic curves and its symmetry properties, which I'll illustrate in a moment, made it possible to establish secure communication without having to exchange quite as much data at the beginning of the discussion. So let me just illustrate the principle behind what all of these methods do, and then we'll come to the actual symmetries involved. So I want to describe a kind of, this is really a toy example. So this is going to be a kind of fake situation, but let's imagine how might two people have a discussion where they can somehow at the end both have the same secret information that a third person listening in could not equally well obtain, because you'd think they are privy to the same information. So suppose you have a secret number, which you don't tell anybody, but you tell the whole world 2 to that number, okay, which is this, right? Now, many of you or some of you may know about logarithms, and if you do, forget about it. All right, this is a toy example. Let's pretend you didn't know anything about logarithms. Okay, so in particular, telling somebody 2 to the a does not compromise a. Now, in reality, there are these things called logarithms, and if you tell somebody 2 to the a, you can figure out what a is. But let's pretend for a moment that this operation of raising 2 to a power kind of doesn't reveal what that number was by any mathematical method. Okay. Now, I have my secret number, which I'm going to have to secretly tell you is 48, but pretend I didn't tell you that. And I raise 2 to my number, and I get that thing. Okay. Now, you tell everybody this, but you keep A. I tell everybody this, but I keep B. And now we can both do something that nobody else can do, which is actually just elementary arithmetic, which is I can take your number and raise it to my secret power, and I get 2 to the AB. You can take my number and raise it to your secret power, and you get 2 to the BA by the laws of exponents. These are equal. Okay? So by each of us using the other person's public number and our secret exponent, we're able to compute this thing. All right? And if we pretended that revealing this did not compromise the security of A, we've now both arrived at a certain number that nobody else could compute. Because, well, we have 2 ways of getting at it, but each way requires, okay, public information, but some private information that only one of us has. But in the end, we both get this common number. Okay? Now, in this particular case, so this is like a joint secret, and you can imagine once you have one secret in common, you can bootstrap on that and then set up a secure link. Okay? But just to illustrate, well, okay, it's a kind of big number. Okay? So you, of course, don't do these things by hand. All right? But in any event, this is a toy example. Because in reality, on a computer, if somebody tells you 2 to the a, you can use logarithms to figure out what a is. Okay? So that doesn't really work so well. But there's this idea that maybe there's some kind of operation you can apply to a secret number, so that if you tell everybody the output, then maybe 2 different people can each use their secret and the other person's public number and do some mathematical operation and then get the same output which nobody else can compute, because although they may have both people's public information, nobody else has either of the two pieces of secret information. And this doesn't work because of logarithms, but in fact, there's a variant which does work using the theory of elliptic curves. So let me just briefly tell you what these are. So these are a class of special curves in the plane. This is an example, cubic curve here. All right, y squared is x cubed plus 8. And, well, you look and say, oh yeah, that has a kind of nice symmetry around the x-axis. You can kind of flip it around and it comes back to itself. Mathematically, that's just the fact that if you negate y, the equation doesn't change. Okay? But these curves have infinitely many other symmetries that cannot be expressed in terms of operations, symmetries of the plane. They have nothing to do with rotations or reflections. They're much more subtle things that are, in some sense, internal to the curve itself. And I want to briefly describe what is that symmetry. Well, as we said at the beginning, a symmetry is a kind of rearrangement. So I want to describe to you a very non-obvious way to rearrange all the points of this curve. So what you do is the following. You pick some point. Here's the point, 1, 3. And now what I'm going to do is, this is my crutch. I'm going to use this initial choice to give you a kind of tricky recipe to rearrange all the points of the curve. All right, so it's going to be some kind of weird symmetry of this curve. So you pick a point, any other point. And then what you do, any blue dot you choose, you draw the line through that initial red dot, whatever it was. And that will turn out to cut the curve at exactly one other point, the black dot. Okay? And then what you do is you then do one more thing. You flip the black dot across the x-axis, and then you get this purple dot. Okay? So this is our symmetry. You go from the blue dot to the purple dot using this fixed red dot. Right? So you choose this, and then for any blue, you draw a line, intersect, new point, and flip. Okay? So blue to purple, that's the rearrangement of the points on the curve. And this works because of special properties of these kinds of equations. Okay, and so this is our symmetry. And notice it doesn't matter whether you do red and blue or blue and then red, because the line between the blue and the red points can't tell the difference which one you chose first. Okay, so this is this operation we'll call this P star Q. You start with P, and you do this complicated maneuver, and the purple output we call P star Q. Right? It's kind of like addition, but not really. Okay, this is the amazing miracle, and mathematically, this is a serious theorem, totally non-obvious. If you chose 3 different points, and you start drawing, 8, 9 different lines, very complicated, at the end, the points you get are the same, whether you do P and Q and then R, or Q and R and then P. Okay, this is a kind of amazing property of this complicated procedure, that if you apply it to a triple in 2 different ways, the parentheses don't matter, just like addition. Okay, this is a very serious theorem. Okay. And the remarkable thing is, well, let me skip this tangent step, all right? But let's just say, here's what we're going to do. You start with any red dot, pick an initial point. So let's even pick the point itself, and then the line between the point and itself is the tangent line. You draw that, you flip, and you get a green dot. But now you do it again. You draw another line through the new point through the red, get a new guy. Flip, you get the cyan dot here. Great. Now again, you draw this point back through the red point. You do it again. Well, that now is off the page. You flip, and then you get a new point. Ooh, it's getting complicated. Okay? But with this fixed red point, you keep, each time you get a new point, you play the game back to the red point, and you get new points over and over and over again. Okay? So this is a very weird operation of the curve, starting with an initial point, and you generate these new ones over and over and over again. And this is what's going on inside the symmetry of elliptic curves. And so let me just briefly summarize. Inside your smart card, okay, there is an elliptic curve hiding in there. Okay? Actually, the elliptic curves that are used, there are 15 that were recommended by the NSA as being particularly well suited to these applications. Now, needless to say, as we now know, maybe they had other properties that people didn't know about that made them well suited to do other things. In any event, this operation of adding a point to itself many times, which will denote like AP, all right, it behaves just like multiplication against numbers. Okay? The difference is there's no analog of logarithms, there's no analog of elliptic addition. If you have a private point and you tell somebody 5 times that point, all right, there is no practical method in a reasonable amount of time that can reconstruct the point. Okay? So this does not fall into the problem with the logarithms. Okay? Well, as I said, the elliptic curves that are used, okay, maybe one should change them now, but this is the game. the bank has its secret large number, and the smart card also has its secret large number. These are off the grid, and then there's a point that everybody knows. The bank computes the point against itself b times using its secret b, tells the world this. Your card does the same thing with the public point against a times. This is the analog of exponentiating. Okay? But telling the world these points does not compromise the actual multipliers because there's no analog of elliptic logarithms in this setting. And then each person takes the other guy's public and multiplies against their private. And in the end, again, you both get the same point. Okay? So in the end, we both have this point that nobody else can compute, because to do this, you either have to have somebody's public and your private number, or your private and somebody else's public number. But anybody else only has the two public points, AP and BP. They can't get their hands, right? They can't get their hands on the multipliers A and B themselves, and so this does not compromise the security. And that is the information that's exchanged every time you buy something over the internet or use a smart card, and that gives you the secure link, modulo these complications with the NSA. Okay? So that's the symmetry of the elliptic curves. And there are many other places where symmetry has come up in mathematics, and then many years later, right, it was discovered that those symmetry principles actually could be applied to real-world problems. Okay? But often the mathematics came a long time before. Okay? But you have to keep in mind, it's hard to predict what math will be useful. Okay? So this was a physicist at Princeton in the early 1900s. We don't need to teach group theory, okay? Which is the mathematics of symmetry. Except later, right, the whole classification of elementary particles relied crucially on group theory. Okay? But who can predict that? Okay? So anyway, those are some references, so I'll stop there.
While Professor Conrad answers a question or two, do you want to do the, you want to plug in there? Oh, go ahead with this question first. Do you answer any, he'll be happy to answer one or two questions. Are there any questions?
So if you take a point of finite order on the elliptic curve,
Yeah.
does that cause any problem with this?
No, the curves that are used have, let's say, very large order. So you have to find elliptic curves where the point can multiply itself many, many times without coming back to the beginning. So one has to find these curves in a good way. So those NSA supplied examples were instances of this. Whether you trust that they don't have other hidden back doors is a different matter. Yeah?
Is there any advantage of quantum cryptography over this scheme? I mean,
Yeah, so you're saying if they ever develop quantum cryptography, what will they replace this with? So there are definitely, the RSA system will break down. But I'll say that I know that cryptography experts have already developed, they have waiting to go improvements on these systems that, to everybody's knowledge, are resistant to quantum cryptography attacks. But they are more expensive to implement. So people have been working on finding replacements, so they have things ready to go if that should ever happen. But at the moment, these are more efficient, so there's no need to implement it. Yeah?
Is this lecture on YouTube?
Is this lecture on YouTube? No. But
would you consider putting it there?
I don't know, but they videotaped it, so
You should go to our website, the IMA website, and you'll be able to. Any quick questions?
yeah.
Is that Escher film you showed us on YouTube?
No, it's on the website. Oh, it's too bad they took the computer down. The thing is called the Drusta effect. If you just type in Escher and elliptic curve into Google, you'll quickly find that web. So the website by Lenstra and DeSmit, they have some applet there which will generate these things. So maybe it's also on YouTube, but there is a website dedicated to this, which you can find using Google.
There's one question there.
Ceramics and crystals have a lot of symmetries,
Yes.
right? The way they're put it.
Yes.
That's more on the 3D. Can you contrast the 3D symmetries
3D?
to three-dimensional?
Oh, three-dimensional. Yeah.
But you mostly talk about two-dimensional symmetries here.
Right. Yeah, no, so the chemists certainly have a lot of use for three-dimensional symmetry, and the mathematics that's relevant to that is a subject called representation theory. And so that is, yeah, let's just say that's a more sophisticated structure than any of the things that I've discussed here. But you can certainly use, I mean, how to say, you want to figure out the structure of a molecule, just by understanding how light reflects through it. And if you know something about its symmetry properties, you can reconstruct some information about the geometry. But you have to talk to crystallographers, but they certainly have to study representation theory. But they do it, I guess, in terms that were maybe partially rediscovered by the chemists. Because it's often the case that when you take sort of the scientists who need some mathematical ideas, they may have rediscovered some of it themselves, framed in the way that they use it. And then maybe it's hard for us to communicate with them. But they use representation theory. Okay.
Other questions? So what we're trying to do here is set up a poll, a very quick poll, but it looks like we're stuck.
It's coming. So
Yes.
yeah, maybe we'll just explain a little bit what we're trying to do here. We're trying to get some feedback from you, and the way that we're going to do this is in real time. So we're going to actually use people's cell phones. If people can maybe take out their cell phones and turn them on, we're going to put some questions on the screen. Very excited.
Does this work? Does this kind of cell phone work?
Yeah.
Oh, even a dumb phone?
Even a dumb phone. I have a dumb phone before. So we're going to need you to text in your responses.
You have no bars.
You have no reception.
Is it possible to participate from a paintball?
Well, if you could get the paintball to text, you could probably do that.
Can we just text on here and then bring our cell phone physically to you if you don't have bars?
Yeah, you can do that too.
Oh, this is very dangerous.
Okay.
747,000.
No. Okay, so how this works is you can see, I'm sorry, it's not really centered right now.